Welcome, class, to our first screencast lecture, Chapter 11. It's on liquids and intermolecular forces. Start off here on this first page with some Lewis structures because it's something that will need a little bit of review to fully understand the Lewis structure. To understand intermolecular forces. So I'm going to jump here to some of the definitions to talk a little bit about intermolecular forces. And really, they are the forces in liquids that hold the particles together, and they're responsible for the characteristics of liquids, a few of which are listed here. So what I like to tell people when I start talking about intermolecular forces is to be sure to be able to distinguish between an intermolecular force, ER, and an intramolecular force. So this is what we're talking about right here, this squiggly line. So it's the force that exists between a molecule, say, for example, hydrochloric acid, which has a very negative portion of the molecule and a positive portion. And it's the attractive force that exists between those two different molecules that is the intermolecular force that gives it its characteristics. And so then there are three types of intermolecular forces. There's the dispersion, the dipole-dipole, and hydrogen bonding. So before we go any further to talk about the intermolecular force, I'm going to just do a quick little review on Lewis structures and what they are and why we need them. So really what the Lewis structure is, it's a structure that shows the distribution of electrons in a molecule. So if I had something like methane, so the first thing I would have to do is count my valence electrons. So I know carbon has 4 valence electrons. Each hydrogen has 1, so 1 times 4 gives me 4 more, giving me a total of 8 valence electrons. And so then I distribute those around the molecule. Each dash represents 2, so 2, 4, 6, 8. And so what I see here is that I have a very symmetrical molecule, right? So the symmetry of the molecule is going to tell me something about the force that would exist between two of these molecules. And then if I look at a Lewis structure for a different type of molecule, ammonia, I do the same thing. I count my valence electrons. I end up with a total count of 8. Then I distribute them. And then what I see here is something very important, is that I have an extra unshared pair of electrons, and that's going to make the molecule very polar and therefore cause it to set up a different type of intermolecular force than I would see in the methane example. And then another example is water, and water ends up, well, they don't all have 8 valence electrons, but the first examples do. So I would do the same thing here, distribute my electrons, and I end up with 2 unshared pairs, making this very polar. So it's the polarity of the molecule, the size of the molecule, or the non-polarity of the molecule that's going to determine what the intermolecular forces are and what effect those forces have on the characteristics of that substance. Here's one that's a bit more complex. It's ethyl alcohol. I go through, an example of how to calculate the valence electrons. 2 carbons, 4 each. There's 8 there. 5 hydrogens, 1 each, 5 there. Oxygen has 6 valence electrons. Hydrogen has 1. Total of 20 valence electrons. I distribute them according to all of the rules and laws, which for drawing Lewis structures, which is that carbons always have to have 8 around them. Hydrogen could only have 2. And then the rest get distributed as unshared pairs. But again, remember, carbon never has unshared pairs around it. So that's just a quick review. Hopefully you remember your Lewis structures from Chem 1. So I'm going to go on to the third page. So on the third page here, I give you some good details about the 3 different types of intermolecular forces: the dispersion force, the dipole-dipole force, and then on the fourth page, I go into the hydrogen bonding force. And so just something, some of the things I want to point out about, let's say, a dispersion force. So the dispersion force is the weakest of all of the forces. Every sample of molecules has the dispersion force. Some molecules only have dispersion, while other types of molecules could have, say, a dipole-dipole or hydrogen bond force. And it would also include dispersion. So I always like to say, when in doubt, molecules have dispersion force, but they don't necessarily have more than the dispersion. It depends upon its polar nature. So one of the things we talk about when we talk about a dispersion force is how polarizable is the molecule. And even though it could be a very symmetrical, non-polar molecule, how big is it? And that's important to note, because the larger the molecule, the stronger the intermolecular forces are. And so if it has a lot of electrons, we say that it's polarizable. Okay, so then we would look at a couple of different types of molecules when we're talking about something like the dipole-dipole interaction. And if I look at something like acetonitrile, which has a molar mass of 41, and I look at propane, which has a very close to similar molar mass, but then I look at the boiling points of each of these, and the boiling point for acetonitrile is significantly higher. And why is that? So I can't just always judge the strength of an intermolecular force based on molar mass. I really have to look at what type of, what category of intermolecular force is it in. So if I look at the acetonitrile and I did a Lewis structure for that, I would find that it was very polar, very non-symmetrical. Well, the propane was very polar. So I would find then that the propane only had dispersion forces, while the acetonitrile had both dispersion and a dipole-dipole. And that's what would cause it to have the higher boiling point. So that's a significant piece of these intermolecular forces, is what is the boiling point of it. Okay, and then we'll go to the hydrogen bonding force, which is the strongest of all of the forces. And this one's easy to recognize only because it only forms when hydrogen is bonded to fluorine, or hydrogen is bonded to oxygen, or hydrogen is bonded to nitrogen. And then you can see where I place these squigglies, where the hydrogen bond force would set itself up. It's going to be in between a portion of the molecule that's positive and a portion of another one of the same molecule that's negative. And so that gives you an idea of how that hydrogen bond force forms. So again, dispersion forces are the weakest, and the hydrogen bonding forces are the strongest. Okay, sorry. So hydrogen bonding, then the next page here, I just compare the strengths of the three types of intermolecular forces. I want to highlight this table. It's a nice table that gives you a comparison of all of the forces that exist and their relative strengths and the characteristics. And then the last one that I want to mention is the ion dipole force, which you'll see on this chart here. And while it's not really considered an intermolecular force between covalently bonded molecules, it is a force that exists in ionic solids. where cations are attracted to the anion in an adjacent atom. So it really depends all on the polarity and the size of the substance. Okay, now here on page 6, I'm going to ask you to really just go through these 3 definitions on viscosity, surface tension, and then the last one here on page 7 is capillary action. So they're very important characteristics of liquids that I think have some real practical applications. So I would like you to know what those definitions are and how the intermolecular forces affect those characteristics. So I'm going to stop there and go to another screencast for the rest of the lecture.